That will work, I think.
All right, welcome to the Signal and Information Processing Seminar for spring semester 2015. As you know, there are several ways in which you can find out what's going on in the seminar. First of all, there's a listing online on ifp.illinois.edu/seminar. Second, if you're on your cell phone and don't want to go to the listing, you can always bring up Twitter, and you can if your network connection works, and search hashtag DSP seminar, and you'll get whatever was posted for the DSP seminar recently. In this case, I posted that today is how to teach signal processing, and I actually posted a link to my abstract online and to the slides that I'll use for the talk. Feel free to please, if you like Twitter, then please tweet talks. Whatever's interesting to you, go ahead and put it up there. Comments on what's coming up or on what has happened. Right now, there are some interesting asynchronies between the talks. But please go ahead and tweet the talks and say whatever's interesting to you about them, and or forward any that are interesting to you to forward. So what I want to talk about today is a topic called how to teach signal processing, and my goals for teaching this topic are fairly straightforward. I'll go ahead and present it from here, I guess. All right. So I'm going to give a presentation today that's sort of a meta presentation, right? I'm not talking specifically about something technical today. I'm talking about how to communicate technical ideas, and my objective in doing so is really this. This guy is my father-in-law, Shigeru Hasegawa. I actually never met him. He died 3 years before I met my wife. He had a degree in philosophy, and he taught computer science, which means that he thought a lot about sort of the philosophy of communicating interesting technical concepts to people who have a particular reason to learn them. And one of the aphorisms that he's apparently used quite often in Japanese, this is my English translation of it, was if you can't write it, you can't think it. This is my interpretation. Clarity of communication enforces clarity of thought. So what I'm going to talk about today is how to teach signal processing from the point of view that if you are able to clearly communicate your ideas in signal processing, that's a way of measuring the degree to which you're actually thinking clearly about the algorithms that you've developed and about the criteria that you've developed. And so one of the purposes of this semester, of this seminar, this semester, will be to encourage you to present your own work. I think there are too many people signed up for me to require everybody to present their own work, but I encourage you to contact me to present your own work in order to clarify exactly what is your own work, or to present somebody else's work, to go into the literature and find papers that are find a paper that's interesting to you and present that, with the idea that that in the process of presentation you will be able to clarify your understanding of that material. So if there's material that you really desperately need to understand in depth for some research that you're working on, teaching it is a great way to understand it in depth, and I want to encourage you to take advantage of this seminar in order to do that. Here's an outline of the talk with almost everything grayed out. I'm going to start out by talking about the relationship between research and teaching, because any time that we talk about teaching at an R1 university, at a Research 1 university, we have to talk about why do we even care about teaching? This is only a university. We don't care about teaching so much, right? And then I'm going to talk about how to teach, and in this part of the talk I'm actually going to do what I just said. I'm going to present to you largely somebody else's work, and specifically I'm going to present to you the how-to wiki on how to teach, except for adapted for our particular problem, which is the problem of communicating technical ideas to a technical audience at a place like the University of Illinois, or at a place like ICASP or Interspeech or CBPR, right? Or at a job talk, or in any other environment in which you need to communicate technical ideas. So So if you look up research and teaching, you come up with interesting articles. There's this is the journal, something from the Journal of Engineering Education in 2007, and these are specific quotes from that article. And these authors of Felder, Brent, and Prince, Felder, and Brent surveyed a couple of dozen other articles, sort of with this mission statement. They said, in principle, the research-teaching nexus relates to ways in which research supports teaching and also ways in which teaching supports research. And people are often saying that you should, debating this question, should you send your children to a large research university? They'll interact with fantastic faculty there, but they'll do so in very large classrooms. And so, on balance, does one get a better education at a large research university or at a small teaching college? And the answer is, it seems to me that it basically doesn't matter. Two main findings come out as a summary of all of the literature. The first finding is that when you normalize for all, when you control for all other parameters that affect the quality of teaching and the quality of research, there's no correlation at all, really R equals 0, between the quality of an individual's research output and the quality of their teaching, as judged by for example, student performance and student surveys. There is a slight negative correlation between the quality of research that a college does and the quality of the student experience at that college. So that this bullet point, so for the individual there's no correlation. For the institution as a whole there's actually a slight negative correlation. Attending a college whose faculty is heavily research-oriented increases student dissatisfaction and impacts negatively on measures of cognitive and affective development. This is at the undergraduate level, and what this is basically saying is that all else being equal, being in a large college, you are more likely to become dissatisfied and alone. One of the things that's controlled, of course, is that's statistically controlled in this result is the quality of the people, the background and accomplishments of the faculty who are teaching you, and I think that might be enough to null out this effect to make this also an R equals 0 effect. So essentially, we have no evidence that at all that that research improves undergraduate teaching. There's Prince, Felder, and Brent argued, and actually the American Academy of Engineering Education has argued since that there is strong evidence that research has the potential to aid teaching, and that there are individuals who are leveraging that potential. And in particular, one of the National Academy workshops makes the claim that education is actually changing. And as graduate students, of course, you already see this daily in all of your courses, right? That education, even at the undergraduate level, is less and less a place where you go in order to sit in the class and take notes, and it's more and more a place where you go in order to learn specific abilities and skills. And learning of those skills takes place both in and out of the classroom in a variety of different ways. And so what we do when we stand up in front of the class, it matters far less than what we ask you to do. And I had here a bullet point that I've taken off that says that engineers have understood this for a very long time, in the sense that every undergraduate, even every introductory undergraduate class in engineering, we as professors make the assumption that what you do on your homework matters a whole lot more than anything that we say in class. And there is actually research evidence to support that claim. But there's the other part of the Prince, Felder, and Brent abstract that they said they weren't going to study at all, and that's the question of whether teaching supports research. This question is, right, so we know that research doesn't support teaching. There's an R equals 0 correlation. But does teaching aid research? For this, there's a lot less published research asking, can you say that measures of good teaching actually improve the quality of the research that the same person performs? There's very little published research on this, but one study was published by Felden, Pugh, and Timmerman, where they actually took, they did a longitudinal study. They took graduate students and they statistically assigned them to a group that was going to have to do some teaching that semester, and a group that wasn't going to have to do any teaching that semester. They had them write up experimental abstracts and methods at the beginning of the semester, and they had them write up experimental methods and abstracts at the end of the semester, and then they shuffled them and blinded them and took the names off and asked faculty members at universities to rate the quality of the hypothesis, the clarity of the hypothesis, and the degree to which it seemed to be innovative and possible. And the finding was that the students who spent part of their time during the semester teaching had a greater gain between the beginning and the end of the semester in the clarity of their hypotheses than did the students who didn't spend any time teaching. And so here's, in case you want a reason, here's what I would say is the first positive correlation that we have suggesting that you should spend some time teaching during your graduate career. That in fact, learning to present material clearly actually permits you to learn to think more clearly. The other way in which teaching aids research is exemplified. I don't think there's been any controlled study on this, but here's an example. There are these guys named Plato and Pythagoras that you might have heard of. They lived a few thousand years ago, and we generally argue that Plato was the first philosopher and Pythagoras was the first mathematician, at least in the Western world, right? Plato was famous for founding the Academy in Athens, the first institution of higher learning in the Western world, and a lot has been said about there's this comparison between Plato and Aristotle. Aristotle was the scientist, and Plato believed in this other world that all ideas come from, and so his philosophy has been discredited in all of its details, and yet in its scope, it's been the opposite of discredited. Whitehead, for example, once noted that basically all of European philosophy is a series of footnotes on Plato. You could take Plato's dialogues and string them together into a bookshelf, and then you could take every other piece of work that's been called philosophy in the past 2,000 years and put it in with a link to one of the pages in Plato that's essentially trying to explain in more detail. Pythagoras, you could say, invented mathematics. You know that he clarified the relationship between the length of a string and the frequency of the note that it plays, and so he invented essentially the idea of frequency as a mathematical concept. He, of course, created the Pythagorean Theorem, that a squared plus b squared equals c squared. And what's really interesting about Pythagoras is that the only reason that you've ever heard of his name is because Plato wrote about him. He founded, we don't even know what it was called. He founded an organization that's often called the Pythagorean Brotherhood, which was a secret society that taught its secrets to those who were, it was almost a religion. It was a mystical society with a lot of very strange beliefs about reincarnation and about other things. They taught their secrets to members of the society and made a point of not saying anything about their beliefs to anybody outside of their society. And the reason that you've heard of him is because several hundred years after he lived, there were a few Greek philosophers who started to write down some of the things that they had overheard as being possibly parts of the beliefs of the Pythagoreans. As far as very, very few of the people who were actually members of the Pythagorean Brotherhood actually wrote anything at all. It was people like Plato who had heard of some of the ideas of that brotherhood who then wrote it down, which is the reason that you've heard of it. All right? So does teaching aid research? Founded a university and became the most important philosopher in Western history. Founded a secret society and would have been entirely forgotten if it weren't for the first guy. All right, there's case study number one. Case study number two, a little bit closer to our time, is this guy, who's I think when you think of socially inept mathematical genius, you think of the white hair, right? You think of Einstein, right? So people think, so when I ask, was Einstein a good communicator, somebody who's walking down Times Square, as we saw at the beginning, would probably say, well, no, he was kind of this mathematical genius, so of course he wasn't a good communicator. In 1905, Einstein was working as a clerk in the post office. He had no formal education to speak of. He was working as a clerk in the post office and read everything he could get his hands on, and decided that he understood a few important concepts better than any of the people who were writing about it at the time, and started writing articles and submitting them to the only journal that he knew of, which was this Annal of Physics. And in 1905, they one after another, they chose 4 of his articles for publication. that created, those 4 articles established the following field: the field of the quantum theory of light and electromagnetics, the theory of Brownian motion, which is the original theory upon which all of modern communication theory and stochastic signal processing is based. Right? If you've heard of this thing called white noise, this was the paper that that invented white noise. This theory called special relativity that eventually was developed into general relativity, which is our understanding of the relationship between all of the forces of the universe at long distances. And this formula equals mc squared, the fact that the energy of an object depends not just on its kinetic and potential energy, but that mass is itself a form of potential energy, right?
The 4 articles are all published in year 1905.
Yes.
In this year, he published 4 papers.
Yes. In this year, that's why they call it the miracle year. Annus Mirabilis means miracle year, right? So, yeah, it's the year that you could say created 20th century physics. And this is the year that, right? So 1905, Einstein published these 4 papers that were read and understood by a sufficient number of people to move him eventually out of his job as a clerk at the post office, for which the Austrian post office will forever be upset. So, right, so our research and teaching, does research aid teaching? Does teaching aid research? To a large extent, there's an R=0 relationship. There's no correlation between them. Researchers need to be observant. They need to be skilled at drawing inferences. They need to be tolerant of ambiguity, and they need to be able to drill through the ambiguity in order to determine what pieces of knowledge would help them to dispel the ambiguity. Teachers need to be good communicators. They need to know something about psychology. Specifically, they need to know the conditions that promote learning. And then the second phrase, an expert at establishing those conditions, that has less to do with one's knowledge of psychology than it has to do with one's ability as an actor or a singer, right? And then needs to be approachable and empathetic. These are not opposite personality characteristics. These are completely orthogonal personality characteristics. There's no obvious correlation at all between column 1 and column 2. And so what I've argued in the past 10 minutes is that there's a couple of things that are left off of that table. First of all, that if you can't write it, you can't think it. This is, I think, the underlying statement behind the Felden et al. Article that teaching supports research because teaching supports your ability to generate clear and testable hypotheses. And second, that researchers who communicate effectively actually have greater impact. If you're able to communicate your ideas by writing them down in an article, by communicating them in an oral presentation, teaching is practice at communicating difficult technical ideas clearly. And for that reason, if you want your research to have any impact beyond the code that you're writing, then it's worthwhile to spend a little bit of time teaching. All right, how to teach. And here I'm going to do what I said I would do at the beginning. I'm going to work almost entirely from an article online. This is a WikiHow article that was originally authored by Melissa Gannis, who's a pre-primary education, is or was at that time a pre-primary education specialist, a PhD working in San Diego. She started out talking about how this is an art, so it's not, teaching is not really a science, but it's an art that's rooted in science. It's an art that's rooted in behavioral sciences. This article then is divided into 11 subsections that are listed across the top there, but let me see if I can get the outline. The ones that I'm going to cover here are the first 6 and then the 11th. Identify the crucial skills that your audience wants, set goals for for how you want to go about teaching it to them, develop a detailed lesson plan. All of these happen before you actually begin teaching. And then engage the students while you're teaching them. And then, this is the only one that's a lecture, right? The classroom lecture is engage students. And then during or after that lecture, you will allow independent exploration, and at points in the future when you have continuous contact with the same audience or the same people, reinforce learning and continue to learn yourself. And so let's dive into the WikiHow. Here's how we go about determining the skills that you're presenting to an audience. So here's what you should think about the next time you're writing an ICAST paper. How do I go about teaching my audience to read? Right? Or no, let's back up. What is the step number one, identify crucial skills, in the context of how to teach, asks, think about what skills your students need in order to make it through elementary school. What specific skill is it that you want to teach your audience, that you want your audience to come away from your talk with the ability to accomplish? So let's adapt that to the task of communicating to a technical audience. I've listed here the underlying skill that I think I was trying to get across in some of my past conference presentations at NIPS workshops and at ICAST and so on. But I think that those talks weren't as good as they could have been because I didn't start out with this formulation. I started out saying, oh, I have this cool research result. I want to tell this research result to the audience. And what the WikiHow suggests is that that's the wrong place to start. The place to start is to say, by the time I'm done with my talk, I want every member of the audience who is paying attention to be able to adapt an automatic speech recognizer to a new voice using eigenvoice decomposition. Right? I want to explain the algorithm in enough detail that they understand where that algorithm comes from and how to go about coding it and how to go about doing it, or how to train SVMs to detect acoustic landmarks. Right? If you think about embedding that skill within the minds of your audience members, it changes in subtle but important ways the way in which you organize the rest of the talk, which is why it's step number one. Step number two is to set goals. Now that you know what you want your students to be able to do, figure out which skills will be necessary to get them to those larger skills, and what you need to say in order to communicate those skills. So let's take one of those particular skills. Let's say I want to teach my audience to detect acoustic landmarks. And the way that I've decomposed this is with a why, what, and how, or put another way, with derivation, algorithm and methods, and applications of that particular skill. Your audience needs to know what they can do with the skill before they have any motivation for learning it. They need to know how to go about performing that skill, but they're not going to understand how to go about performing that skill unless they learn where the components of that algorithm came from. Right? The reason why we teach derivations is because we want people to understand why the steps of the algorithm are what they are. Derivations might be specific, might be differentiating a particular optimality criterion, in which case you want your audience to understand why that optimality criterion makes sense. Or they might be a proof of an upper bound on a particular mutual information criterion, in which case you want your audience to understand what that mutual information criterion is and why it makes sense. Or it might be that that's the way that the auditory nerve works. And so in that case, you want to make sure that your audience understands where they would go in the auditory physiology literature to look up information about that particular function of the auditory nerve. Right? And then from these, we get particular steps in the algorithm, which you want to make sure your audience understands by the end of the talk, and you want to make sure that they understand how to apply it. That's the least cute and exciting picture of the several pictures. There are several levels of detail in any teaching, including teaching of technical skills to a professional technical audience, or including teaching kindergartners. And this is the level that actually gets the most attention in the how to give a good talk kind of presentations. So here's one that there are a couple of faculty in our department who always make this sort of a line in the sand that you can't cross. Find out how many minutes long your talk is and make sure that the number of slides is less than or equal to the number of minutes. Right? If you have a slide up for less than 60 seconds, then nobody is going to understand what's on it. Right? Nobody is going to understand anything that's written in less than 20-point font. So if you have anything written on your slide in less than 20-point font, it's background clutter. If you have anything written on your slide in 12-point font, it's part of the background picture. It's not part of the intelligible text of the slide. And anything past the third label on a graph, the third symbol in an equation, or the third item in a list. I actually restructured this so that it was two embedded 3-item lists to try to exemplify that. And I'll come back to this too. There's a much more detailed structure, for example, for a thesis. There's a standard structure where we say the first chapter is motivation, the second chapter is background, the third chapter is research goals, the fourth chapter is methods, the fifth chapter is results, the sixth chapter is discussion, the seventh chapter is conclusions, and there's specific content that should go into each of those. But at the larger level, the structure of a scientific paper comes down to tell them what you're going to say, and then say it, and then tell them you said it. All right, get people involved. Show them pictures of duckies and kittens. Specifically, right, for engineers, we get one more kind of communication modality than kindergartners get. The poor kindergartners only have pictures and words to deal with, and we also get equations. And there's a reason why we use equations. The reason is because it's another way of communicating a difficult concept. If I tried to communicate everything using pseudocode, then the only people who will understand what I've communicated are those who read pseudocode quickly, right? So it's useful to communicate ideas in several different modalities. Equations are a compact way of presenting an idea, which is compact and hopefully clearly defined, if you define all of your symbols. And for those who are quick at reading equations, they'll understand immediately what you're saying. For those who aren't quick at reading equations, they won't understand what you're saying. There was I gave a talk at the conference on laboratory phonology last summer, where people were actually tweeting continuously during the talk. There were people who were kind of making a habit of tweeting the talks throughout the conference. And one of the tweets during my talk was, "This talk is really hard to tweet because of the equations." So there will be some people in your audience who don't follow the equations, so you have to give them something else. Give them a graph that has one key idea that people will rapidly get from that graph, or examples in the form of a story. With regard to story, there's a great book that I'll recommend to you as it was recommended to me. There's a book called Made to Stick. This is actually, the idea of stickiness is based on another social scientist's work, and these two, I forget, Chip Heath and Dan Heath, one of whom is a social scientist and one of whom is an entrepreneur. The brothers came up with this, with a wonderful series, a book full of case studies built around this acronym that's invented to make it impossible for you to forget how to make people remember your ideas. Stickiness is the why some ideas survive and others die. Stickiness is this word that was invented a few years ago for the property that some ideas have of sticking in your brain and being memorable. And they summarized the research of one or the other of the Heaths with this acronym SUCCESS, saying that simple, unexpected, concrete, credible, emotional stories stick. So when I'm talking about stories, I'm talking about some kind of narrative formula, a narrative formula that's emotional in some sense, that arouses some kind of response, not necessarily happiness or anger or disgust, but some kind of emotional response. More often sympathy than anything else. Sympathy in the sense of identifying with one of the characters or identifying with an idea. You could tell a story in which the protagonist is an idea, right? In which is as concrete as possible, which includes, doesn't just talk about some people like partial differential equations because they're kind of cool, but actually gives specific names of people who have used them for specific purposes, and which has some unexpected twist at some point, and yet is concentrated around just one idea. This part goes back to the movie City Slickers. Have any of you seen the movie City Slickers? Okay, so Preeti, what scene am I referring to? City Slickers is about five friends from Manhattan, lawyers and bankers, who decide to spend a summer vacation traveling, riding cows from Texas to Montana or back. I can't remember which direction they're going, and they're all phenomenally impressed with the old cowboy who kind of volunteers to take them on and leads the expedition. And at one point, one of them asks him, "So, what is your secret? Why are you so successful and so happy?" He says, "What's the secret to life?" Yeah. What's the secret to life? He says, "This. The secret to life is to choose one thing that you're going to focus on and to stick to it." All right. Trouble with the app. Allow independent exploration. Yeah, my classrooms look like this sometimes. So, for example, this could go into the section on engaging students. But I want to get back to Plato. Here's the actual dialogue in which Plato presented the Pythagorean theorem. If you'll go through the dialogue, so in this dialogue, what happens is that Socrates is visiting with a friend of his, another philosopher by the name of Meno, and he and Meno are discussing what is virtue, and they've come to a point in the dialogue when they've determined that virtue is a kind of knowledge, that it has to do with knowing what is the best thing to do at any given point in time. And then they're debating, is virtue taught or is it innate? Is it something that people naturally have from birth, or is it something that can be taught to them? And Socrates denies that this is a distinction worth making. And he says, let me show you why this is not a distinction worth making. Do you have any slave in your house who's never had any education at all? And so Meno calls for a little boy, and Socrates starts drawing figures in the sand and says, okay, look at this. What's this? The boy says, that's a square. He says, how long is that side? He measures it, and he says, okay, this is a 4-foot square. All right, now let's draw another square next to it. Now let's draw another square next to it. And if you work through the dialogue, you discover that he actually proves essentially the Pythagorean theorem for the case when a and b are the same. He proves that a squared plus a squared is equal to 4 times a squared by drawing a bunch of squares next to each other and then taking the diagonal and drawing another set of squares and then showing him essentially that if you chop those squares into triangles, you get an equality of area. And this is wonderful. This dialogue has spawned fanfic, and here's the best one that I've seen.
The Pythagorean theorem states that if the legs of a right triangle have lengths A and B, and the hypotenuse has length C, then A squared plus B squared equals C squared. To prove the Pythagorean theorem, remove 4 copies of the right triangle from a square with side length A plus B, as shown in the picture. The part of the square that the triangles don't occupy, shown in red, has area A squared plus B squared. Now remove 4 copies of the right triangle from the square in a different way, as shown on the right. The part of the square that the triangles don't occupy, again shown in red, this time has area C squared. Since the red area in both pictures is what's left over after removing the same 4 triangles from the same square, the 2 red areas must be equal. So A squared plus B squared equals C squared.
There's actually a lot of different proofs of the Pythagorean theorem available on YouTube. You can search for visual proof of Pythagorean theorem. This is the one that I like the best.
Equals C squared.
This is the one that I like the best because it's, number one, it's general. It's actually more general than the one that Plato published because it covers the case when A is not equal to B. And number two, it doesn't involve any additional algebraic manipulation at all. It does have equations and pictures and a story, right? They're all there. We have the story of drawing this square and taking out triangles. But the critical relationship that A squared plus B squared equals C squared is entirely done by chopping these triangles out of a larger square. I like this one as an example of using multiple modalities to engage an audience and of allowing independent exploration, because in the sense that there are at least dozens of people who have published proofs of the Pythagorean theorem online. Shouldn't be presenting this for the web. See how far I've got. right, so so the canonical example of how to allow independent exploration is the advice that's given in any regular teaching class. If you go and take TA training, for example, they'll tell you that one of the important things that you should try to accomplish, even though it's difficult, is to get the members of your audience to answer questions and ask questions. And I haven't done a very good job of asking you questions in this class, but is this a class? In this seminar?
Mm-hmm.
I haven't done a very good job of that in this seminar, and partly that's because I'm sort of modeling what you can do in a place like ICAST, where you don't really have that option. If you're standing in front of a large lecture hall presenting your own research to a group of professionals, they will all come and ask questions at the end during the scheduled 5-minute question time. They won't be asking questions during the lecture. And in that kind of environment, it's actually really difficult to have any idea whether your audience has understood what you've said. And second, it's really difficult to actually get them to ask questions, right? And so we have to kind of somewhat more generally, somewhat more ambiguously define what we mean by audience participation, I think. How can you get your audience to participate in your ideas when they're not willing to say anything? And I'm going to leave that up to you as an exercise for the audience. The next topic is to reinforce learning. And here's again Dr. Mel Gannis's words, unless they've been edited by somebody else since then. Occasionally revisit old material. This will solidify and reinforce the skills that a student has gained, much like learning a language requires study every day. I like telling my sophomores this quote from Galileo, where he said that the book of God is written in the language of mathematics. So in fact, learning difficult technical concepts is very much like learning a new language. And the WikiHow Online has suggestions of specific times during a regular teaching cycle when you would go about revisiting that material. Let me present a different time, and this is another aphorism that was given to me by somebody who taught a course on politics and the media that I took in 1996 at MIT. He was fun to listen to because he liked to do things like comparing his profession, which was journalism, to jazz music. He said that he said it's a continuous means of asserting oneself as a human being and an agent to the world. In other words, reporting is a way of acting. In the particular aphorism that I want to tell you about is this one. I've mentioned it before. If you want anybody to remember what you say, then you need to say it at least 3 times. You need to tell them what you're going to say, and then you need to say it, and then you need to tell them that you've said it. It's just how it is. People don't remember things that you say only once. Finally, keep learning. Read up on your craft. Read the latest journals and papers from conferences to keep up with the most innovative methods. This is kind of this is almost not necessary to mention to this audience, because I think all of us are here because we learn. I like doing sort of decomposition of words into their roots, right? The word student means person who studies. The word professor means person who speaks. And so I sometimes claim to be a professor, but then every now and then I'll claim that I'm a student, because I think that's the more important of the 2 occupations. So I'm done, actually. I've told you, I think, why it's worthwhile to learn to teach. It's, the reasons that I think it's worthwhile to learn to teach are that it will improve the clarity of your scientific research by allowing you to more clearly define exactly what hypothesis you're testing and how you'll go about testing it, and because it will improve your impact. It will allow other people to actually understand your ideas. And then I've talked a lot about how to teach, and I love the WikiHow because it has cute pictures, and I like cute pictures. What's really interesting about it is that almost every one of the steps in the WikiHow dealing with how to appropriately teach kindergartners is actually perfectly valid when you're talking about how to give a technical presentation to a large engineering conference. This one that I've often missed in my talks is that you should start out by asking what is the skill that you want your audience to acquire by listening to your talk. And that will guide you in the second step that we often do remember, which is to decide what fundamental understanding do you want your audience to actually acquire in order to help them with that skill. And then second, decide how to actually present it in order to communicate that fundamental understanding. Decide how to go about making sure that people are involved with the ideas as you present them, and figure out how to get them to solve problems on their own using the ideas that you presented. And finally, keep